All right, we've got some really cool stuff to unpack today.
Looking forward to it.
It's all about gravity.
Oh, nice.
And our source material is from Open Educational Resources, Open Source Physics at Singapore.
Okay, sounds interesting.
Yeah, they've got some really fascinating insights on this fundamental force that, honestly, we
Yeah.
all experience every single day.
Yeah, without even thinking about it, right?
Exactly. And today we're going to break it down. We'll even get to play around with a simulation that's on their website.
A simulation. Fun.
Yeah, it's super cool. But first, let's start with the basics. What exactly is gravity?
Right, back to the fundamentals.
I know, right? So our source defines gravity as a natural phenomenon by which physical bodies attract each other due to their masses.
Okay, a pretty straightforward definition. But what's really mind-boggling is that this attraction happens at a distance.
At a distance.
Yeah, no touching required. Like right now, the Earth is pulling on you and you're pulling back on the Earth.
Whoa, I never thought about it like that.
And all this without any physical contact. It's kind of wild when you think about it.
So it's like we're all connected by these invisible strings.
Exactly. And this action at a distance is described by something called Newton's law of gravitation. You know, the classic story of Newton and the apple.
Oh yeah, the apple falling from the tree.
Exactly. The source talks about how Newton saw that apple fall and suddenly realized, wait a minute, the same force that pulls that apple down is keeping the moon in orbit around the Earth. Pretty revolutionary, right?
That's some serious out-of-the-box thinking.
For sure.
So how did he turn that realization into a law? The source gives us a formula, but it's, well, kind of complicated at first glance. Something about masses and the square of the separation between their centers.
Yeah, the formula itself can seem a little intimidating, but it actually describes a pretty elegant relationship. Basically, it says that the force of gravity between two objects is directly proportional to the product of their masses.
Okay, so more mass means more attraction.
Exactly. And it's also inversely proportional to the square of the distance between their centers.
Inversely proportional. So the farther apart they are, the weaker the force.
Exactly. But it's not just a simple halving of the force when you double the distance. It's this thing called the inverse square law.
Inverse square law.
Or think of it like shining a flashlight on a wall.
Yeah.
When you move the flashlight further away, the light spreads out over a larger area.
Yeah, and it gets dimmer.
Right. Gravity works in a similar way. The force gets weaker as the distance increases, but not linearly.
Yeah.
If you double the distance, the force isn't just half as strong, it's actually a quarter as strong.
Oh, I see. So distance plays a much bigger role than I initially thought.
It's all about how they relate. Mass is like the strength of the gravitational pull, and distance is like a dimmer switch, weakening the force as objects move apart.
That's a great way to put it. Now, I noticed the source specifically mentions using the center-to-center distance and not the radius of the objects.
Ah, good eye. That's because we're treating the objects as point masses, basically simplifying things. It's like we're shrinking the Earth and the Moon down to tiny dots.
Okay, so it's like a simplification to make the math work.
Exactly.
Yeah.
And speaking of making things easier to understand, you know what else the source has? An interactive simulation.
Oh yeah, we mentioned that earlier. You can actually see how changing the masses and distance affects the gravitational force.
Yep.
So what can we expect to see?
Well, imagine two masses on your screen, right?
Okay.
And there are these arrows between them, representing the gravitational force pulling them together. You can change the size of the masses to make one bigger or smaller.
Interesting.
And you can move them closer together or farther apart. As you make those changes, you'll see the force arrows actually change in size, visually showing you the effect of your adjustments. It's like you're seeing that inverse square law in action.
Wow, that sounds amazing.
It really is. You can even play around with it and create different scenarios, like having one massive object and one really tiny object, and then moving the smaller object closer and further away.
Cool. So I can experiment with gravity without needing a lab.
Exactly.
Yeah.
It's a really fun and insightful way to learn about these concepts.
That sounds awesome. I'm definitely checking that out later. But for now, let's shift gears a bit and talk about escape velocity. The source touched upon it briefly.
Oh yeah, escape velocity. That's the speed an object needs to hit to break free from the gravitational pull of a planet or a star.
So if we wanted to launch a rocket into space, it would need to reach a certain speed to escape Earth's gravity.
Exactly.
What factors do engineers have to think about when they're designing spacecraft to overcome Earth's gravity?
Well, they need to consider things like the weight of the spacecraft,
Of course.
the amount of fuel it needs,
Yep.
and the trajectory, the path it's going to take.
So it's not just about raw power.
Right. It's about finding that delicate balance. And the escape velocity itself, that depends on the mass of the planet you're trying to escape from. The more mass of the planet, the stronger its pull, the faster you need to go to break free.
Wow, that makes sense. It seems like we could do a whole other deep dive just on escape velocity.
We definitely could. There's a lot to explore there.
But for now, I think it's a good point to take a breath and reflect on what we've uncovered so far.
Sounds good.
We've talked about the basic definition of gravity. We've explored Newton's law of gravitation and even touched on this concept of escape velocity.
And we've seen how the inverse square law comes into play and how, the simple simulation can help us visualize these pretty complex ideas.
And don't forget, even though gravity is considered the weakest of the fundamental forces,
Right.
it's still shaping the entire universe.
Yeah. I mean, think about it. Something so seemingly weak holding entire galaxies together, it's kind of a paradox.
Definitely puts things in perspective.
It really does. It makes you feel small, but also connected to everything.
Absolutely.
It's humbling. It really makes you think, doesn't it?
It does. All these forces, like gravity, working behind the scenes, shaping everything around us,
From the tiniest particles,
to huge galaxies.
it's pretty amazing. And it reminds us that we're part of something much bigger than ourselves.
Totally. It's
Yeah.
like we're all dancing to gravity's tune, whether we realize it or not.
Uh-huh. Yeah, a cosmic dance. And speaking of dancing, remember that simulation we talked about?
Oh yeah, the one where you can change the masses in the distance.
Exactly. What I think is so cool about it is how it lets you see the impact of those changes, like right away on the gravitational forces.
Yeah, sounds like a really powerful tool. Can you give us an example? Like, how would you demonstrate that inverse square law thing using this simulation?
Sure. Let's say you've got those two masses on the screen, right? You could start by just doubling the distance between them,
Okay.
and then watch what happens to the arrows that represent the gravity between them. They won't just get half as long, they'll actually shrink to a quarter of their original size.
Wow, so you can actually see how quickly the force weakens as the distance increases.
Exactly. It really brings that concept to life, It's not
Yeah.
just some formula on a page. You can see it happening.
Yeah, that makes a lot more sense now.
Yeah.
So it's really all about the relationship between mass and distance, right?
Right. It's not just about how massive the objects are, it's also about how far apart they are.
I'm starting to get it now. Is there anything else about this simulation that really stands out to you?
Well, what I find fascinating is that this relatively simple simulation can help us understand concepts that apply to the entire universe.
That's pretty cool.
Like, remember when we were talking about launching a rocket into space
Mm-hmm.
and escape velocity? Well, playing with this simulation can actually give you a feel for how increasing the speed of that smaller mass can eventually let it overcome the pull of the larger one. It's like a mini version of a rocket escaping Earth's gravity.
Oh, I see. So even though it's simplified, it still reflects the basic principles at work in the real world.
Exactly, and that's the beauty of educational tools like this. They take these complex scientific concepts and make them accessible and engaging. It's not just about memorizing formulas, it's about developing an intuitive understanding of how things work.
I totally agree. Now, something else the source mentioned was that gravity is actually the weakest of the four fundamental forces.
Right.
Why is that?
That's a question that has puzzled scientists for ages.
Mm.
I mean, think about it. Gravity holds entire galaxies together, right?
Right.
But it's weaker than the forces working inside the nucleus of an atom. Doesn't that seem strange?
Yeah, kind of a mind-blowing concept. So we have this incredibly weak force shaping the entire universe.
It is a bit of a paradox, isn't it?
It is.
And it really makes you appreciate the vastness of the cosmos. I mean, for gravity to have such an impact, despite being relatively weak, the distances and the masses involved must be just unbelievably huge.
It's hard to even wrap your head around it.
I know, right? It makes you realize the scale of things and our place within it all.
Makes you feel both tiny and connected at the same time.
Exactly. It's both humbling and awe-inspiring.
Absolutely. And I think that sense of wonder is what drives scientific exploration.
Oh, for sure.
The more we learn about something like gravity, the more we realize how much more there is to learn.
That's so true.
Yeah, it's amazing how much we've already uncovered about gravity,
Mm.
from the basic definition to its role in, well, shaping the entire universe. But like you said, there's still so much we just don't know.
There really is, and that's what keeps science so exciting. It's all about discovery, about pushing the limits of what we know.
It really makes you realize that even something as, I don't know, as everyday as gravity can still be full of surprises.
Absolutely. And one of the most mind-boggling things about gravity is how it connects us to everything in the universe.
We talked about that cosmic dance before. But what do you mean by connects us?
Okay, so think about this. That same force that's keeping you right here on Earth, it's also the force that governs how planets move around the sun, how stars move within galaxies, and even how galaxies move within clusters.
Whoa, so we're all part of this massive cosmic web,
Hmm.
all woven together by gravity.
Exactly. And that web, it doesn't just extend through space, it also stretches across time.
Across time. What does that mean?
Well, think about the light we see from distant stars. That light, it's traveled for millions, sometimes billions of years, right?
Yeah.
And along the way, its path has been bent ever so slightly by the gravity of massive objects. So when we look at those stars, we're actually seeing the universe as it was in the past, shaped by the same force that's shaping our present.
That's incredible. It's like gravity is this bridge
Yeah.
connecting the past, the present, and the future.
Exactly. And it shows us that understanding gravity, it's not just about, formulas and equations. It's about understanding our place in the grand scheme of the cosmos.
It's about realizing our connection to everything that was, is, and will be.
I love that. And I think that's a really powerful idea to leave our listeners with. As you continue to learn about gravity, remember you're not just studying a scientific concept, you're exploring the very fabric of reality, the force that links you to every star, every galaxy, every single moment in time.
Beautifully said. I think that's the perfect note to end on. Our deep dive into gravity has taken us from a basic understanding of this force all the way to, well, its incredible implications for the universe and our place within it.
Yeah, it's been quite a journey.
It has. We explored Newton's law of gravitation, that inverse square law, escape velocity, and even touched on some of the big mysteries that still surround this fundamental force.
And we learned how even a simple simulation can open up a whole new level of understanding, making these concepts accessible and engaging for everyone.
Absolutely. So, to our listeners, keep exploring, keep asking questions, and never stop being amazed by gravity and the universe it shapes. And hey, there are tons more deep dives waiting for you right here, each one a journey into a new realm of knowledge and wonder. So stay curious, stay tuned, and we'll catch you on our next adventure.